reading day. And I'll try to, yeah, I mean, this will take me, this will definitely busy me for a couple streams. I just wanted to take a look at these, which came across my Twitter, um, kind of, I don't know how you call that, dashboard or Twitter, whatever the recommended things, kind of like just because I'm following Jens Eisert, and then I think he shared these, and a bunch of other people commented on that, and I kind of went through the abstract, which I forgot, and I have to go through this again. And I thought, I'll do that because I definitely want to read papers from time to time. I think it's interesting, especially when it comes to kind of resource theories and things like these. And there's gonna hopefully gonna do something in there about entanglement as well. And the whole thing about quantum complexity is something that I've recently stumbled upon, and that it's not, I guess it does not refer to the computational complexity, like the big O notation and stuff, but it's rather something about the complexity of a state. So how complex or how complicated it is to build a state, maybe, or maybe this complexity is going to do with complex numbers. I don't know. We'll figure it out, I guess. But let's see. I mean, what do I expect about this paper? To be honest, I don't know. I just want to see if that, you know, it's always one of the things where I think reading this paper sometimes kind of uncovers little aspects and little corners of the quantum mechanics and quantum computing world that ones didn't know before. And so, you can then either turn them into rabbit holes, or, you know, they enrich at least sort of the knowledge about the landscape, um, in this case. So um, let's go straight into these, and let's kind of do the typical abstract conclusions and figures, because I did scan this through, and to be honest, um, for my taste as a non-expert, and the subject matter, there seems to be quite some. Okay, so but that's the appendix. So let's see how much we really want to get, deep into the appendix, actually, because it's a proof and complexity structure proof. I mean, eventually, it would be cool to go through these things and kind of double check them, just for for the sake of just practicing that as well. But this is quite complicated. This is definitely something that I wouldn't be able to approach right now. I'm not at least not just like that. I guess if I'd spend time enough, I'd eventually go through something. Let's see. Okay, so that's actually, there's a long appendix, and then but the paper goes down until here. Okay, some conjectures. Let's see. Um, let's see. There's not so many figures and whatnot, but I guess from the title, that's to be expected. I guess it's more about describing a resource theory. Because so let's kind of recap what it says. Quantum complexity is emerging as a key property of many body systems. I like that it's about many body systems, including black holes, topological materials, and early quantum computers. So what are topological materials, though? Actually, I've seen that term come up a couple of times before. Topological materials. Uh, you know what? I'd like to actually see that. Topological insulators are a new state of quantum matter. Topological materials. This is probably too. What is this? Topological materials. Topological insulators are a new state of quantum matter with a bulk gap and odd number of relativistic direct fermions on the surface. The bulk of such materials is insulating, but the surface can conduct electric current and well-defined spin texture. Okay, but what are these useful for? These exotic materials could find applications in electronics, catalysts, and quantum computing. Trying to figure out a way to build even smaller transistors than already existed, making nanowires of bismuth and nickel that were only 4 to 10 atoms thick. He still doesn't precisely know why the wires had such thing, high resistance and therefore low conductance, but function get around the conductance. Okay, so are these just? I guess I don't know where the topological comes from. The idea of topological materials grew out of work in the early 70s when physicist Michael Kosterlitz of Berners used the concept of topology to explain why superconductivity happens in certain materials at extremely low temperatures, but disappears at higher ones. Topology, but topology, that's a math thing, isn't it? Maybe physics? There's maybe a physics concept to it attached. The manga. So in mathematics, topology is concerned with properties of a geometric object. Okay, but I'm interested in the context of physics. Topology is relevant to physics in areas such as condensed matter physics, quantum field theory, and physical cosmology. The topological dependence of mechanical properties in solids is of interest in disciplines of mechanical engineering and material science, electrical and... Okay, so I guess it's just the study of the, like, sort of the surface of the objects, right? Of the materials. Okay, the arrangements of how the molecules are structured and things like that. Okay. Topological materials. So I guess this is maybe when you take a look at materials from a topological perspective, maybe rather than just like pure, I don't know, chemical composition or something like that. A state's complexity quantifies the number of computational gates required to prepare the state from a simple tensor product. I guess a simple tensor product would be just the basic, say, initial starting state, like the all zero state, for example, right? The greater a state's distance from maximal complexity or uncomplexity, the more useful the state is as input to a quantum computation. Okay, so that's interesting, right? So I'm curious to know in what terms is more useful in terms of like being more resistant to decoherence, being more, I don't know, resistant to noise. I don't know. Maybe highly complex states. Yeah, well, of course, right? Because highly complex, like to prepare complex states, you could use a lot of gates, and so that means you better have like really good error correction. Maybe, I don't know. Maybe it's a bit naive, but separately, resource theories, simple models for agents subject to constraints, are, I don't know how to pronounce that, burgeoning in quantum information theory. English. English. Why doesn't this catch the thing in the first place? Burgeoning. I'm not German native. I know what aufkeimen means. I want a definition. You know, never search for translation. Just search for definition of a word. Growing, expanding, developing rapidly. Okay. We unite the two domains, confirming Brown and Susskind's conjecture that a resource theory of uncomplexity can be defined. Resource theory of uncomplexity. So I guess by resource, because there's the resource theory of entanglement, as in like how useful is entanglement, right? And I guess a resource theory dictionary of psychology. I don't know if that's a good source. don't know what's going on with my internet. A theory of interpersonal relationships holding that the amount of resources, laugh, yeah. Okay, but I guess you can translate that, right, in terms of like, so you have different agents, you have different things that you want to do with, and then you've got like resources, and so that in a way constrains what you can do. The more resources you have, the more you can do things like these. Like in terms of entanglement, I think it's something along the lines of the the highest amount of entanglement from a resource theory perspective is the entanglement that allows you to kind of, from that place, it allows you to move to any other possible state, both entangled and not entangled, right? And the minimal resource is when there's no entanglement because you can't get to the whole entangled state space only with like local operations, right? Yeah, I think something like that. The allowed operations, fuzzy operations, are slightly random implementations of. Okay, so the allowed operations, fuzzy operations, are slightly random implementations of two cubic gates chosen by an agent. We formalize two operational tasks: uncomplexity extraction and expenditure. Their optimal efficiencies depend on an entropy that we engineer to reflect complexity. The entropy being the measure they're going to define here to reflect that complexity. We also present two monotones and complexity measures that decline monotonically under fuzzy operations in certain. Yeah, okay, so I guess the idea here is you've got a state, right? And so the more you apply these the more operations you apply to it, the less resources you want to have, right? Because I guess that's the point. It's like that's how you define this complexity or uncomplexity, right? It's what's the minimal. What was that? The amount of gates required to prepare a state from a simple tensor product. I forgot what a monotone is in mathematics. It's some kind of type of. God, can't I just get this stuff in English? Yeah, because I'm in incognito mode, right? English. Yeah, but is it gonna remember that? I guess a monotonic function is probably a function that just kind of a monotone is a function between ordered sets that preserves or reverses the given order. This concept first appears in calculus or the theory. Okay. It is not monotonic. Okay, I guess what it means is that it preserves the order or reverses it from with respect to the dimensions, right? So if this is the input and this is the no, this is the input, this is the output, or the other way around, like you can see that for higher, so, so the more you go here, the farther along this axis you go, the farther down along this axis you go as well from an output perspective. Whereas here it's not like it just messes up the order, right? Which is what you want when you define this kind of stuff, because you want to make sure that the more the more, of course, the more operations you use, the less resources you have. That's because the more complex then the state becomes. This unleashes on many-body complexity the resource theory toolkit from quantum information theory. Cool. So let's see. Let's take a look at just quickly the sections, how this is structured. So this seems to be a bit of an intro, resource theory thingy, and then we have a figure here. It says state complexity and its geometry. So a pure n-qubit state, psi, has an exact complexity C of psi equal to the least number of gates required to prepare psi from 0. And here, what's interesting is that they pick the set of they pick the set of gates to be random 2-qubit gates. I don't know why. Because maybe, okay, because I mean, this definitely allows you to include entangling gates. And maybe the thing is this kind of allows you to also include things where you apply the identity in one qubit and then another operation at the bottom qubit, you know what I mean? So kind of it covers all the cases in general. Thank you. The state's exact uncomplexity, so equal to the least number of gates required to prepare psi from the zero state. The state's exact uncomplexity is a distance C max minus C. But I'm curious why this is defined this way, because I would intuitively say that Cmax doesn't have to be unbound, like it doesn't have to be bounded, right? Like you can just you can go nuts if you want. Like you can have like, okay, unless you'd be saying that, you would obviously not consider circuits that are redundant, or circuits where it's like, okay, so if you combine these gates, but this is equivalent to do these other gates, which is like less amount of gates, and that defines, and so there's a maximal complexity. So you want this difference to be as big as possible to the maximal n-qubit state complexity. So why is this interesting? Why is this e to the power of n? Why? Okay. In a revision of Nielsen's geometry, complexity curves the state space negatively. Complexity curves the state space negatively. Applying a gate corresponds to moving a unit length along a direction in this geometry. Yeah. Most directions point toward higher complexity states. To transform into a generic state psi prime, psi likely must pass through the zero state. No significantly shorter path exists. Oh, that's interesting. So what this is saying is that that likely to go from psi to psi prime, what you have to do is then compute psi and then compute psi prime. So kind of like there's not always right like a path that goes directly from psi to psi pi directly that is shorter than I'm computing and computing. B. I don't quite understand why in a complexity curves the state space negatively. What is reference 15? Good luck understanding any of these. I'll just open it and see what happens. There should always be a way to go back to the reference. Applying a gate corresponds to a unit length along a direction in this geometry. I mean, yeah, you kind of have. So you're in a geometry, right? Like in a space that is like the complexity space, and so you're like at a given point, say, and then, of course, applying gates will always move you somewhere, right? But it almost feels like why would that space? Okay, yeah, because depending on the gate you apply, right? Like the thing is, because I was thinking like why isn't that just kind of like a one-dimensional space, right? But it's more like, but that's not true, right? Because depends on the gate you're applying, that might limit the choices you have for later gates to apply, and so kind of each step in the process constrains sort of the next steps, right? And if you make the wrong decision, then you might end up with a much more complicated path. Yeah. Consequently, uncomplexity is desirable in quantum computation. Given a complex psi to prepare desired output psi prime, one must uncompute, that's what I said, psi to this and incurring an overhead. So that's like, yeah, you kind of have the overhead cost of doing that, which is basically, you know, the cost of psi prime, to be honest. Our resource theory introduces randomness, green shaded regions, into the gates. Such gates tend to increase the state's complexity. Okay. Using the resource theory, okay, no, sorry, that's already the figure. So what else do we have here? So we have definition of the resource theory of uncomplexity. Here's the definition, and I see already some kind of SU4, blah, 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 so things which I'm not familiar with, but I'll definitely have to get into. Definition 1, every fuzzy gate is defined in terms of an arbitrarily chosen 2-qubit gate U. The fuzzy gate U is selected uniformly, randomly, according to distribution of these that satisfies conditions I and II above, 1 and 2 above. Every composition of fuzzy gates is a fuzzy operation. Okay, so these are just definitions. What else do we have? Complexity entropy. The complexity entropy of an n-qubit state, I guess this rho, is the minimum blah, 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 of the trace of Q. Oh god, that's complicated. Okay, so here they go and explain that a little bit. Take a look at these. Complexity entropy. Suppose that, oh god, of course, you might still have like mixed states in the whole thing, right? Let the number of R of performable gates be high compared to the number of gates needed to prepare psi. So you are approximately, and that's the gate psi. So most tensor factor Q projects into a low dimensional subspace, so it is small as it requires in this extreme case. I don't know why. What is the trace here? What's got the trace to do here? But that might be interesting because at least will kind of maybe give me some insights in some unknown things. Yeah, it's good. Okay, so this is about the actual theory. Then there's a theorem. So there's some protocol that extracts. Okay, so figure 2. Let's see what figure says. Operational tasks of uncomplexity extraction and expenditure. Operational tasks of uncomplexity extraction and expenditure in the resource theory. Since gates are fuzzy, the agent can perform only less or equal to R gates, lest the state grow too noisy to be useful. Yeah. A. Extracting uncomplexity from a state. Okay, so the extracting and expanding. Extracting is like the like uncomputing, and extracting uncomplexity from a state. Rho 1 applies the fuzzy gates. The number of qubits left in the state 0 is the extractable uncomplexity, which equals the complexity entropy of rho. Yeah. Given enough zeros, an agent can spend uncomplexity to imitate rho. The agent performs R fuzzy gates, preparing the state believed by a computationally bounded referee to be a rho. Okay, yeah. Are the fuzzy gates there just to kind of account for errors? I don't know, maybe. It's not obvious to me, right, that you have to pass through zeros. What the fuck is this spam in the chat, man? Bye, viewers and bigfellows.com. You're getting a ban. Give me a second. How can I ban people? Can I ban people? Yeah, ban, timeout, mod, ban. You are, sir, are banned. That's not the kind of messages that we want in the chat. Cool. So that is not so obvious. Something to come back to, that you actually have to go through the all zero state. I mean, let's think about this for a second. So if, yeah, so actually it might make sense, because if you define, so if you know that you have a state, but that's because of the way it's defined, right? So the way the whole theory is defined, because if you're saying, look, the resource theory, this whole resource theory thing is like, I'm going to define complexity as in the amount of gates it takes to move from an all zero state to my desired state, right? And the complexity of a state, psi, is the minimal amount of gates that take you from zeros to that state. So that's the minimal. So yeah, so actually, if you reverse the thing, like if you have a state, psi, you want to go to psi prime, like it's almost like saying actually the path from psi to zeros and zeros to psi are like both minimal in terms of you're adding two minimal quantities, and so probably that is the minimal path, probably. But I don't see why that has to always be true. Like I can have a state, right? Even just like say the Bell state, and I can say, look, like I only need to apply one operation to get to this other psi prime, right? But if I would uncompute and compute, I would actually have more. So it probably is one of the things where it's true for most of the cases, but it's not generally true. But I don't know. I'd like to see if the paper gives a bit more details into this in the text. Theorem 3, so there's a monotonicity, whatever, however that's pronounced. Okay, so you want to know this function is always, it's monotone. Conjecture, so theorem 2, let rho denote an arbitrary n-qubit state, let Rn, I'm so bad at Greek letters, as both, and assume that there's been 2 times R, and this is against an error or something, for every n qubit state can be imitated with, whoa, why? Okay, gotta unpack that. Conjecture 1, the negentropy cannot increase under fuzzy operations. Okay, so and already conclusions are here already. We can go through these now. And then there's the Uncomplexity extraction proof. That's for the details. Okay, so what do the conclusions say? We have confirmed Brown and Susskind's conjecture that a research theory of uncomplexity can be defined. The research theories allowed operations balance random evolutions, which model chaotic systems with the agency in resource theories. The agent chooses operations to perform. Using the resource theory, we formalize the uncomplexity expenditure and extraction, the task's optimal efficiencies. We quantify with the complexity entropy that we introduce. Finally, we identify 2 fuzzy operations, monotones, and regimes. As well introduces into quantum complexity, the resource theory toolbox has garnered success across quantum information theory. Our resource theory deviates superficially from 2 holographic conventions. What the hell, like holographic conventions? We invoke the circuit complexity instead of Nielsen's geometric distance. Correspondingly, gates act in discrete time steps, whereas Hamiltonians act continuously. Our model is motivated by quantum information theory, where discrete gates from circuits, the closeness of circuit complexity to Nielsen's complexity, and random circuits modeling the chaotic evolutions. Reasons suggest that our results might extend from fuzzy gates to continuous time evolutions. What is this Nielsen's geometric distance? What is this? This work establishes several opportunities for future research. First, the complexity entropy evades the shortcomings described below. Definition 2, this entropy can quantify the efficiencies of computationally restricted tasks, such as data compression with few gates, beyond uncomplexity extraction and expenditure. Computing the complexity entropy may be difficult typically. However, the complexity entropy properties and applications to information tasks and one-shot thermodynamics will be explored elsewhere. What is one-shot thermodynamics? Second, the complexity entropy suggests an operational answer to the question undergoing active research, how to define mixed state complexity. Oh yeah, that's interesting. That's what I said, right? It's because in theory that includes mixed states as well. Complexity quantifies the difficulty of extracting uncomplex zero qubits. More precisely, the complexity entropy can anchor a version of the strong complexity introduced in 73. One would evaluate the complexity entropy. Similarly, theorem 4 may generalize to a wider regime. Fourth, the resource theory framework suggests many questions locked in 16. For example, can allowed operations in interconvert any two states asymptotically if arbitrarily many copies are available. Furthermore, we anticipate connections with other resource theories focus on the difficulty of implementing unitaries. The resource theory of magic. What? What is this? That's cool. Fifth, the resource theory can impact holography, many-body physics, and quantum computation. One might reframe black hole paradoxes quantitatively in terms of resource extraction and expenditure. Also, though fuzzy gates involve little randomness, they can... Oh, give me a second. Someone's at the door. There you go, back. Cool. Um, yeah, we'll have to loot here soon. But basically, what else? We're doing one might version black hole properties continuously. And that's it. Uh, I'm kind of missing, I'm missing in a way to, I think I grasped the general structure and idea. Obviously, then you just have to go through the way things are defined and understand that, but maybe that's less relevant for me right now. Although I will do that in the next stream this week. I like to understand a bit more the whole thing with the going through zeros and whatnot. Um, but again, like I don't fully understand. I don't fully understand or can take from what I've read at least sort of how that maps to the usefulness in quantum computing, so to say, right? Application of resource theory of magic states. I forgot what magic states was. Where? Uh, one shot, thermodynamic, and one shot. No. Good luck finding anything here. The geometry of quantum computation. Is this Nielsen like the Nielsen from Nielsen and Tron, the book? Mm, yeah, I think so. Uh, these are quantum processes, but I don't know really what the usefulness applied to quantum computing. You know, application resource theory for magic states twofold. And tolerant quantum computers. Where was I? Let me see. Quantum computation as geometry. Come on, I forgot the paper I was in. There we go. The resource theory of uncomplexity. We consider a system of n qubits denoted by the power z operator by the eigenvalue vector let denote the one qubit identity. Fuzzy gates form the building blocks of the allowed operations. The agent can attempt to perform any two qubit gates and SU4. This is something that I've also have to at some point get into in terms of the mathematical background of all this. Is it category theory? I guess the groups and whatnot, right? Any two on any two qubits, our results generalize to two scenarios in holographic literature. First, each gate can couple. Second, the target gates can form a discrete set. The gate implementation suffers from noise as follows. Fix an error parameter denoted by is not zero. I'm getting lost in here. I'm getting definitely lost. I'm trying to understand where is the usefulness of the resource theory of uncomplexity, right? Like it would allow me to sort of order and sort states by their complexity, right? So you kind of can, like, yeah. Yeah, I guess it's more like a theoretical application. I mean, it's practical as well, right? In terms of, to be honest, I don't know. I mean, resource theories are useful, I guess, to discuss about like optimal transactions, optimal things to deal with, optimal ways to deal with transformations and things like this. or even like decidability at all, right? Like, can we do something with that state? That can something be done with this state? It's like, no, it's too complex. Like, or yeah. I guess that's what these theories uh, are for, or what is the resource theory for? I mean, that is like, otherwise. Resource theory, quantum resource theories. Oh, are often high versatile and powerful framework for studying different phenomena in quantum physics. From quantum entanglement to quantum computation, resource theories can be used to quantify a desirable quantum effect, develop new protocols for its detection, and identify processes that optimize it. Yeah, okay, cool. So okay, so that answers my question, I guess. A different phenomena in quantum physics. From quantum entanglement to quantum computation, resource theories can be used to quantify the example quantum effect, that develop new protocols for its detection, and the process that optimize its use for a given application. Particularly, activities have revolutionized the way we think about familiar properties of physical systems like entanglement, elevating them from being just interesting fundamental phenomena to being useful in performing practical tasks. The basic methodology, because for the entanglement resource one, it kind of makes sense because this whole thing of how useful is this resource, because I know at least I've read that certain states will help you, will actually, yeah, act as catalysts, right? So will help you in conjunction with another state to reach another state. So this is something that's why that seeing entanglement or building a resource theory around entanglement kind of makes sense. But building a resource theory around just the complexity of a state, uh, like, I'm missing the point there, I think, either way. Uh, so you have free states, you have free quantum operations, and then, yeah, you have restrictions placed over the place, and the studies how infinite processing tasks become possible using these restricted operations. Uh, Quantum reference frames appear to have great similarity or deeper structural levels. There's already a recent general framework for quantum resource theory focusing on common structural features. Okay, that's just like a meta thing about quantum resource theories. Um, which still, like, that might be an interesting thing to take a look at, to be honest. Like, it's probably more general about how you go about defining a resource theory for these stuff. Cool. Okay. So, but it's still, I've got two open questions. One is sort of uh, like a concrete application of these, which I'll see if I can dig one out, and then some details, right? So I can dive into the technical details. Uh, Probably spend a couple more streams on these. Anyway, it was fun reading through the general structure of the paper. Cool. See you next time. Soon. Any of these days. I haven't really figured out a schedule yet because I can't. With the babies at home, I can't. I tried, but I'll try to do like I'm trying to do 2 to 3 streams a week. That's my goal, and it seems to be working so far. So cross fingers that's gonna work and stick for a while. Bye bye.